Yeah, thank you very much for the introduction, Ben. So I like to talk about the Parity architecture today, which I've done already quite often in my life. But I also want, in the end, to give some new flavors, in particular in the stuff that we heard today in the morning about using arbitrary atoms for optimization, which I think is a very interesting direction also for the Parity architecture. So why do we put constraints and optimization problems in the title? So let me start with some of the features that the Parity architecture really offers. And going back to the very basics, so typically if we want to solve optimization problems, we think about things like this. So for example, this graph partitioning problem, where we ask how can we partition this graph such that the number of edges connecting the two subsets is minimized. This is probably a problem that many of you have already seen. And the way we solve this is we introduce a cost function, which is then the energy of our physical system. In this particular case, we do this by introducing spins, which now sit on the nodes. So this is an important thing. The nodes of the graph become the spins. And then we find a Hamiltonian which has the ground state of this problem as the energy function. So in this particular case, this Hamiltonian will consist of two parts. One which tells us that we have a subset of equal size, and the other one which tells us that the number of connections is minimized. And this is an example where the problem Hamiltonian that comes out is indeed of the form of a qubit problem. So it has the form of pair interactions in single body terms. However, there's many other problems out there, and these are the problems that you find, here it's called industry relevance. Once you're looking at more complex problems, they are often not in the form of qubit already, but they might have higher order terms in them. For example, not just pair interactions, but also free body terms. Now, or four body or five body terms. And this is something that we can still cast into a quadratic problem by decomposing these higher order terms into pair interactions. And the example that is shown here, so imagine you have five so-called logical qubits or five problem qubits, and you have the pair interactions, which are the lines, and then you have two free body terms. This would be something that's already maps quite nicely to a quadratic problem. So on the right hand side there's the quadratic version. So in this case we only had to add two additional auxiliary qubits. However, if you have a larger problem and all connected higher order terms, this overhead becomes quite large. And then, and this you do on the logic problem, right? You still have to encode it afterwards. And the other thing, and that's also something I would like to talk about today, is constraints. So imagine, so the second word in qubit means unconstrained, right? So if you, in addition to having an unconstrained problem, also have additional side conditions, they enter as constraints in the problem, and they can come in the form of products or sums of products. So for example, if the constraint is sigma 1 times sigma 2 is plus 1, this would be a product form. Or if you have a sum, and that's something that's very common in optimization problems, then this is something that gives you an additional overhead because you have to write it in this Lagrange formula where you have the sum minus the constraint squared, which then again allows you to minimize an energy. Now, what I would like to present, as many of you probably know it, but I still do it, is this the parity transformation, or the LHZ formula. And here I would like to give an outlook what this is. So on the left side is what I would call the qubit paradigm. So this means that we cast any problem to an all-to-all connected pair interacting graph, where we have different mapping methods. And what is shown on the right side is the parity architecture. And this is fundamentally different in the sense that there's no pair interactions. There's only four-body interactions. So all the qubits that you see here are the green dots, and in between the red dots, these are the couplings, and there's no pair interactions in the system, there's only 4-body terms. And what's particularly remarkable is that the only thing that we have to program is the first part, so the single-body term, which means that all the interactions become problem independent. And this is something that's very attractive for hardware platforms. We will see later that you can use this, for example, for using global lasers if you have atoms, or we have already seen yesterday talk by NEC, for example, how we can realize this really in hardware. So the interactions become problem independent, everything is encoded in local fields. The price that we pay is that we have to introduce for each term in the Hamiltonian 1 qubit, and we have to somehow encode these constraints. Now, on the other hand, as I will show in a few seconds, we can encode any higher order terms with this, so we can encode arbitrary optimization problems, so not just quadratic unconstrained problems, and we can constrain, and we can encode constraints in a very interesting way. So, let me start with the transformation itself, so let me derive it indeed. So how do we go from this QUBO version to the parity version? The first thing is that we introduce the parity variables. So these are variables that measure the parity between two logical qubits. So on my slides, the logical qubits will be always the blue ones. So these are the ones that we have in the problem. And the green ones are the ones that we have on the chip. So these are the physical qubits. And I labeled them 0 and 1, but they're really just errors, so it's just to distinguish them. And what they are is the product of the sigma c part. So if the spins are pointing in the same direction, it's plus. If they're pointing in different direction, it's minus. And now if we start, let's say we start with the example that we have seen, a QUBO problem, so a quadratic problem, then this would have a term like this, J sigma c, sigma c. And if I now translate this into these new variables, which have now the hat on top of it, they represent the product of two, which means here is already most of the magic happening, because we can already see that an interacting term has become a local field term. And the Jij, which is previously the coupling element, has now become a local field element. And so this is already more or less the crucial part here. Also, by the way, there is no calculation in between, so you can literally take the number in front of there and put it there. However, there is now a problem, so there is no equation in between. And the reason is that the number of degrees of freedom is wrong, right? So on the left side, we have n degrees of freedom, and we have k programmable elements, which is n times n minus 1/2. While on the right side, we literally have now k, so n times n minus 1/2 degrees of freedom. So this means we have to somehow get rid of k minus n degrees of freedom, which means we need k minus n constraints. So the idea is basically that we enlarge now our Hilbert space, and we have to reduce it again by introducing k minus n constraints. So we can ask ourselves, so what are these constraints? And it turns out these constraints can be constructed from closed loops in the original problem. So imagine or take this closed loop here, so we have 3 spins, and we have closed loop 1, 3, 2, 3, 1, 2. And now let's make a translation table between the parity variables and the logical variables. So let's say we have the configuration 1, 1, 1, which means all the spins are pointing up. Now let's translate this. So each of the edges has parity plus 1, which means this translates 1, 1, 1 translates to 1, 1, 1. Now, let's take another example. All spins are pointing down. Now again, 1 and 2 point in the same direction, 2 and 3 point in the same direction, 1 and 3 point in the same direction, so this again translates to 1, 1, 1. Now we can continue this, let's do one non-trivial example, so down, down, up. So 1, 2 point in the same direction, 2, 3 point in a different direction, 1, 3 point in a different direction. So down, down, up translates to up, down, up, and so on. So we can make the full truth table, and if we do this, we may encounter this example here. So we want to translate this back now. So let's say we have 1, 2 up and 1, 3 up, but 2, 3 down. And if you want to translate this back, you will find that there is no configuration which actually has this truth table on the right side. So if we analyze this, we find that on the right side, in each closed loop, the number of spin downs has to be even. So there's no way that you can reach a configuration which has an odd number of spin downs. And intuitively, this is very easy actually to see, because if you start with all up, so the first example, and you flip one blue spin, you always flip 2 green spins. So you can never reach on the green side an odd number of spin downs. Now, this is already a constraint, because this tells us which configurations are not allowed. And the only thing we have to do now is we have to translate this sentence into an energy. And this is also very easy, because these are spins. We just need to multiply them and put a minus in front. And a large energy constant C. So if you multiply these 3 spins, then if you have an odd number of minus ones, this gives you an energy penalty. If you have an even number, it doesn't give you an energy penalty. And now you can do the same question or the same trick for any closed loop. So the first observation is, in a closed loop you have as many greens as blue spins. So this means this is always consistent. And this rule is true for any closed loop that you find. So if you take, for example, this closed loop, what comes out is that the constraint is this 4-body term. If you have a loop of 5, it will be a 5-body term and so on. So this means we have now a lot of possible of these constraints. So we can take any closed loop in the system, and now we can ask for another few things. So first of all, we would like to have the minimal number of constraints, so we would like to have k minus n, and not millions or something like this. Secondly, we would like to have every edge in one of the constraints, because this allows us then to make the system fully programmable. And the third one, and that's basically the only challenge in the whole thing, is we want to select these closed loops in such a way that the physical chip that comes out has no long-range interactions anymore. And when we started this, we actually thought that this is basically impossible, you know, because we start with an infinitely connected or infinite range system, and we want to map this now to something which has no long-range interactions. However, it turns out that there is exactly one solution for that, and this is the one that I would like to show. And the building block is this closed loop here. So let me start it again. So we start with 2, 3, and put the 2, 3 here. And so the way I order this now is I order them by these lines, and these lines are the difference between the two numbers. So 2, 3 would be on the line S1. Then the next closed loop is 1, 3, which translates to 1, 3, 1, 4, 2, 4. So I always get 1 to the right, 2 left, 3 to the right, 2 back. So this is my first constraint, and on my physical chip, this will be then my first 4-body term. Now I take the pattern and move it 1 to the right. And what I see then is that the 2, 4 is already there, right? So I can recycle it, and I just add to 5, 3, 5, 3, 4. So I continue with this and go through the whole chain, and then I have, in this example where I have 6 logical qubits, I get my first 3 constraints. In total I will need 10 constraints, so now I have 3. Now the next building block is that I take this pattern and stretch it by 1. So now I go 2 to the right, 3 left, 4 left, 3 back, 4 back. And if I now look at the elements, like 1, 4, 2, 5, 2, 4, 1, 5, I see that 3 of them are already there. So you see that 1, 4, 2, 4, and 2, 5. They are like the upper corner of the lower ones. So I just have to add the 1, 5 on top, and I have again a constraint. So I do this again, go through the whole system, stretch it through the system, and that's why I get this triangle shape, right? Because I will stretch it by 1, so the distance I can travel is always 1 shorter. So I get this triangle. So I have now 6 constraints, I need in total 10. And it turns out the 4 missing ones are actually here in the bottom. So I add 1, 2 on the left side and 5, 6 on the right side. And if I do this, I see that there is 4 free body terms down there. So for example, 1, 2, 1, 3, 2, 3 was exactly the example that we looked at in the very beginning. So that's free body, free body, free. So this means, first of all, if you look at this now, you see that we have used every edge, so all combinations are used here. There's no long-range interactions anymore, so everything is laid out in 2D. It's a nice square lattice. And so to say, the way it looks like is that there is like a line of free body terms, and then there's this bulk of 4 body terms on top. And in the original paper, we have actually added an additional row of qubits which were fixed to +1, and by doing this, you basically remove the free body terms in the bottom, and you have only 4 body terms left. So this is now the final model, so you have a fixed row of +1, and then you have only 4 body terms, and the qubits representing the edges. Now, this has been introduced in 2015, and many people complained about the overhead. So this has a quadratic overhead, which is actually the minimum that you can have. However, if you have a problem which is not all connected, but there's some missing edges, you want to remove them, right? And this is something that would be called a compilation. So this means how can we reduce the number of qubits if we have not an all-to-all problem but less than all-to-all. And before I show the compiler, let me just rephrase everything that I said in one slide. So we have an original problem with number n nodes, k edges, and we represent this now by a system of k of this parity, variables, and k-n+1 constraints. So by the way, in my slides I often say k-1 and sometimes k-1, k-n+1. So this +1 comes in from the symmetry of the original problem. So if the original problem has a local field, it has one symmetry less than the right one, because the right one does not have a global spin symmetry. So this is just a bit. So the way we constructed it then was we need k-1 constraints. These constraints were closed loops, and then we found one particular pattern of closed loops which allow us to make this space for them. Now, let's say we have a system which is not fully connected but less than fully connected. For example, the graph that you see here on the left, so there are several connections missing. For example, between 3 and 6 there is no connection, which means if we translate this, remember that the strength of the edge becomes the local field, which means you simply have a qubit which has no local field. And in this case, if you would just follow the LZ approach, you would have many of these qubits which have no local field, which means they are not programmable and don't contribute to the calculation. Now, what you can do now instead is you can just do what we did by finding these closed loops, again for this specific graph. So you can say, let's take all the closed loops which are possible. So in this case, and now we already know that these loops should be length 3 and 4, so this already helps us a bit. In principle, you could of course also take loops length 6 or anything you want, but we already know if you want to have a square lattice, you should better take 3 and 4. So in this case, these are all closed loops from 3 and 4. And then I can start like putting these puzzle pieces together, right? So I can again translate every edge to a qubit, and then I can start laying them out and see if I can find some form where these puzzle pieces then all fit together. Now in this case, so we have, let's see, so we need k minus n plus 1 constraints. So let's count. So we have 9 edges, so that's 9 lines. We have 6 nodes, so 9 minus 6 plus 1 is 4. So we need 4 constraints, and we have 5 available building blocks, or 5 available closed loops, which means we have to select 4 out of these 5. And it turns out that what you see here on the top is the solution of this. So if you select them in this way and you put them together in this way, you have exactly a compiled chip which uses all the qubits, which has no auxiliary qubits, and has exactly the right number of constraints. So yeah, this is how we can now compile it. Then the second generalization that I would like to show is the pair interactions versus higher order terms. And in order to do this, let's rethink why we actually use these closed loops in the first place. So just to remind you what we did, now we selected these closed loops, and then we had these parity variables which are on the edges. So and what they are simply the product, right? So for example, parity variable 2, 6 is the product of 2 times 6. Then 2, 3 is 2 times 3 and so on. And then on the physical chip, what we have is the 4-byte term of them, right? So we have 2, 6 times 2, 3 times 3, 5 times 5, 6. Which means if we decompose this again, what we see is this is like a product of 8 spins now. And because this is a closed loop, it's trivial that every index occurs exactly twice, because we're back to our original index, so every index occurs twice. Which means this product is always plus 1 if we select a closed loop in a graph which is only pair interactions. Now, and for pair interactions, this is also the only way how we can construct products which are always plus 1. However, we can now generalize this by saying, okay, let's generalize and not look at closed loops or closed cycles in the graph, but let's say what we actually want is that this product here, the last product, is always plus 1, which means that each logic index has to appear with an even frequency. Now, as I said, for a graph, these two statements are equivalent, so there's no other way to select than selecting closed cycles. However, if you have a hypergraph, then the second definition is much more general, because there is, by the way, no definition in hypergraphs for closed cycles, so we needed to generalize this. So this means if we have now a hypergraph which has, in addition to these lines, also, let's say, 2 free-body terms, right? So we have the pair terms 1, 2, 4, 5, and so on. And in addition, we have now 1 times 2 times 3, and 3 times 4 times 5. Now, with our generalized definition, we can now simply create a constraint out of a combination of pairs of two-body and three-body terms, because our only condition is that each logic index occurs with an even frequency. And you can convince yourself that if you have 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, then each index occurs twice, and if you multiply all of them, you always get plus 1. So this means if you now take a graph like this and you would first translate it into a qubit problem and then embed it, you get a considerable overhead. While in this parity mapping plus compiling, what you would get out is just 6 qubits with 2 4-body terms. So again, you can count the number of degrees of freedom. So you have 6 terms in the Hamiltonian, which means you have 6 physical qubits that you have to implement. And then you have k minus n plus 1, which is in this case 2, which means you need 2 constraints. So this is all consistent. And now the examples that we've shown worked without auxiliary qubits. However, sometimes it's also favorable to just add a small number of auxiliary qubits, which is also something that we can do during the compiling process. Now, let me just show you a gallery. So just to show you how fundamental this mapping is. So what is shown here is a few graphs. So they are these are so-called regular graphs, but you can take any graphs. I just want to show them because they're kind of illustrative. So what is shown always on the left side is the logic graph, and what is shown on the right side is the parity mapped plus compiled chip. And what you can see here is that if the graph has a certain symmetry, often also the mapped one has a symmetry. For example, if you take the second one here, this ring or double ring here, this also has some symmetry done on the right side. And for example, here on the right side are some highly symmetric ones. So I find this kind of really beautiful, and it also shows that this mapping seems to be very fundamental. And of course, these are all pair interactions because they are can be easily drawn as graphs. However, you can do the same game with higher order terms. So this is an example where you basically have a bunch of higher order terms, which is something which would really require a lot of physical qubits if we would do this with a qubit map. Now, constraints. Let me say a few words about constraints. So what we've seen so far is the implementation of spin problems without side conditions. But sometimes you may encounter problems with side conditions, as said, some products. And for products, there is something that I find mathematically really beautiful, which I would like to show you here. And let's take again the example that we've seen previously. So this is a free regular graph, by the way. And now let's say we add an additional constraint, and we say that the product 2 times 3 must be plus 1. So as a physicist or as a let's say D-wave programmer, you would immediately say, oh, that's easy, I just need to add a very strong energy between 2 and 3. Now in the parity mapping, you can do something different. You can do the following. You can think again or remind yourself about the condition that you have to select a closed loop such that each index multiplied gives plus 1. Which means, if you now take a loop of length 5, so for example the one on the left, the one that looks like a house, no? So 1, 2, 1, 6, 5, 6, 3, 5, and 2, 3. So this is a loop of length 5, which has this constraint in it. Now if you take this loop and you multiply them, you know per definition, or you've introduced as a definition that 2 times 3 must be plus 1, right? Which means if you make now a constraint only of the remaining 4, we have a valid constraint which also satisfies the side condition. Which means you can now add as a constraint the loop of length 5 into your compiled chip. And this means that you can now select not just from loops of length 4 and 5, you can also select from loops of length 5 which have 1 constraint in it, which become length 4, and loops of length 4 which have 1 constraint in it, which become length 3. Which means you can completely eliminate 1 qubit, namely the qubit 2, 3, and this is somehow hidden then in the fact that in some of these constraints the indices 2 and 3 are missing. And this allows you then to remove 1 qubit per constraint. And with this you can do some crazy mappings. So I have to say that this is reverse engineered, so this is just an illustration. So imagine you have this super complicated Hamiltonian on the right side plus a list of constraints. This would be something that you can cast into such a super simple chip geometry. Now, another form of constraints that we will encounter quite often is that of sums. And here I would like to just show this in a few words. So imagine your constraint, which is shown here, is 2 times 3 plus 1 plus 2, 1 times 2 plus 2 times 3 is some constant. Then what you can do now is, because we have now this compiler which allows us to place qubits, we can now take these 3 qubits and put them next to each other. So for example here the top row is 2, 3, 1, 2, 2, 6, which are exactly the ones that are part of the constraint. And now we can design our interactions in such a way that in our annealing or whatever process we do, we say that the unconstrained part has a sigma x term, so it's allowed to flip by itself. And the yellow ones, they are not allowed to flip by itself, they are only allowed to do exchange moves. Which means if I start now my annealing process in a constraint satisfying state, which is trivial, now I can select a random one, and as a quantum operator I only allow sigma plus, sigma minus between neighbors, my constraint will be always satisfied during the evolution, and I don't have to energetically enforce it, but I can dynamically enforce it. And this is something which requires, of course, compiling, so you have to put your qubits next to each other. And it also requires that your chip allows not just sigma x, but also interaction, like flip-flop interaction. But this is something that many platforms can do. And in combination with compiling, you can do a very interesting mappings here. Right, so due to the time, so these are just some benchmarks which you can look up in this paper. And this paper, in the last few minutes, what I would like to present is details about implementations. So, one we have already heard yesterday, and with this I will not go into too much detail. So NEC and ParityQC are at the moment collaborating in developing this chip, which we, as I said, already heard yesterday, so this is very exciting for us. What we've also heard today is about Rydberg atoms, and here I would like to present now also something new. We have already looked into using the LHZ or this parity architecture for Rydberg atoms in different scenarios. So this paper, for example, shows how we can build a annealer with Rydberg atoms in with two species. So this was a proposal where we mixed two species where the red qubits would act as mediators for these four-body terms. However, if you do this, you can build a fully programmable annealer with having global addressing of the atoms. In a different context, we also proposed how to implement the parity architecture specifically for QAOA. So here, the idea is basically that you can simplify again your Hamiltonians by using QAOA setup where you actually don't need the additional auxiliary qubits by assuming that you can address your digital device individual four-body packets. Now, what I would like to discuss a little bit more in detail is the most recent work from already 1 year ago, 2022, how to use the parity architecture to implement it in this minimal weighted independent set. And this is something that we heard today in the morning, that's why I would like to just show it also. As you probably remember, right, so we had the idea of this minimal independent set is that you map the ground state of the minimal independent set to your actual problem. And this is now something that's of course very interesting for our architecture because it consists of only two building blocks which are always the same and there is no long-range interaction. So it only consists of these four-body terms and three-body terms. So what you see here, for example, is in figure A is the problem that we would have. So the colored things are higher order interactions, and B would be then the compiled chip. And what is shown on the right side is how you would implement one of these plaquettes. And you can do this by 17 qubits, so you have 9 plus 8, no? 1, 2, 3, 4, 5, 6, 7, 8, 11 qubits. And these 11 qubits, they are basically two triangles where both of them represent a three-body term. So the most outer qubits, so the one bottom left, bottom right, top left, would be your logical or your parity qubits. So these are the qubits that have then the four-body interaction. And the construction in between is the minimal independent weighted independent set version of two three-body terms which meet in one point. And two three-body terms which meet in one point is actually identical to one four-body term for the outer two qubits. And the way this works is that there is a local field acting on the central three qubits which has strength 2 alpha, and on the outer side only 1 alpha. And this actually gives you a spectrum which is exactly that of a four-body term. And now, if you add these building blocks together, there's one subtlety which is shown here on the right side, which is you have to compensate for the long tails of your Ripper interaction. And this can be done by adding 2 qubits in between the plaquettes. And if you do this, you end up with a system where you can locally optimize the plaquettes and then in a scalable way just add them up. So there's no additional compensation or anything that you have to do. And now what's particularly interesting about this is, so what we've seen here is still a system where you have a global Ripper laser, but you still need to have some qubits which have global field 2 and some which have global field 1. However, you can also reduce the number you can also remove this, and you can make this completely without any local detuning. And the way this is done is by simply moving the atoms around. So by distorting this triangle from this perfect triangle to something that looks more like a hexagon, you can achieve the difference in the local fields by the interactions between the qubits. So you're basically shifting the energy of the energy levels, and with this you can basically remove the condition that is sometimes in 2 and sometimes in 1. And in addition to that, you can now program the local fields of A and B. So A and B are the 2 outer qubits of your forward term by changing the distance that is shown here. So between A and capital A and small a, and between B. And the same thing, so this is, so to say, one free body term, and then you have the second free body term, which is simply on the other side, so symmetrically, which is shown here in the bottom. So with this, by tuning these distances, we have fully programmed all the local fields, and with this n term in the Hamiltonian. So keep in mind that, I mean, we are already in this parity picture, which means that these local fields, they represent the programming elements of the logical problem, right? Any higher order term. And again, so one can show that this can be done individually for the plaquettes. So these calculations, so there is no crosstalk or anything between them. And what is shown here then on the right side is what comes out as the pattern that we have to implement. So on the top, again, you see this compiled chip with the squares and the triangles. And if you look here at the background, there's again the same squares and triangles because they are representing really the 4-body and 3-body terms that you need for your system. So what you get out is really this simple graph where the programming is now really in the directions, and we have no local detuning, so we have really one global laser. Just to show you the energy spectrum of this, just to see that this is also working. So for this example, what is shown here on the right side is in the first column the energy landscape. If you have no programming at all, so which means there's no local fields, then this yellow line is basically the general ground state of all possible combinations of spins, ups and downs. And once you add programming, the green one is the logical problem, and then the middle one is the physical system, which has exactly the same energy spectrum. As you can see, the blue ones, so these are unphysical states, they can mix down. You can solve this by just adding higher energies, but actually you don't need to do this because in the end you're only interested in the ground state of the problem. Okay, so with this I'm done. I hope I was able to convince you that this parity mapping is really interesting. It's really a different way to look at these problems. What I've shown here was really for optimization problems. This is also something that you can do for universal quantum computing and for digital quantum computing. With the compiling, we can really get rid of the overhead and have minimal overhead, and we can offer different advantages for different platforms. So this is the team. So I would like to mention just a few names. So Martin Landthaler, who is also here, worked out most of the stuff in the Ripple implementation. If you have questions about this, please go to him. This is a picture of the retreat by the company and the research group. So all these people that you see here are working on the parity architecture. And with this, I would like to thank you.
Okay, thank you for the talk, Wolfgang. We are now open for questions.
Thanks for a nice talk. If you go back to your non-local mappings, it seems that what you trade off here is that your circuits physically take up a lot more space in space because you have a lot more kind of, like here for example, you've got big empty spaces. In terms of the compilation, is there a way to minimize the physical space used up in these constraints?
So the space in between, so these lines, they are only necessary for the compensation of the tails. And this is something that we probably need in any of these LIS systems. So you cannot get rid of this by compilation because this has only to do with compensation of tails. So if you look at the logical one, will look like this.
Thank you for the interesting talk. I have to admit I was trying to follow this work for quite a few weeks now, and it's really given me quite additional clarity. So 2 quick questions. Question number 1, if you have a lot of higher order terms, does it get more difficult, sort of like in hypergraphs? Does it get more difficult to file an encoding, figure out exactly where those 3, 4, or more sigma z states have to land on your lattice, and how to connect them in loops?
Yeah, I don't have a real intuition for that. Maybe thinking about how the compiler works, in the end we are basically translating everything in this form, right? So let's assume we have to write a compiler, right? What you would do is, you would always start with the graph, and you would translate this into like a set of closed loops that we have, and then you have to put these puzzle pieces together. And at this moment, you basically remove the labels, right? So you don't even care if it's 2, 3 or if it's 5, 6, 7, 8 or something like this. No, you just have a bucket of these closed loops that you have available, buckets of qubits that you have replaced. So my intuition would be that the complexity of the compiler is independent of the order of the terms.
Okay, so but is that a polynomial time kind of algorithm, or is it
very
there?
Very good question. So the answer is that the complexity of the compiler depends on the auxiliary qubits that you allow. So let's think about 2 extremes. So if you don't allow any auxiliary qubits, then the compilation is either NP hard or not possible. Right? Some graphs just cannot happen. Now, if you allow, in this case, quadratic number of auxiliary qubits, you would just end up with LHZ. So it's order 1. Okay. So exponential order 1, which means if you allow auxiliary qubits, you have somewhere in between the transition to polynomial, and this I think is something that you have in any compiler, that what you want is polynomial scaling, and you have a trade-off between efficiency and how many auxiliary qubits you put.
Okay, that clarifies a lot. The quick follow-up then, if I just look at a mapping and Ising model with a parity encoding on so no higher order terms, just up to quadratic. Do I see this correctly, that you're going to basically end up with at most n squared of those terms, right? Yeah. And then every one of those constitute 9 atoms plus connectors. Do you not end up with roughly the same overhead as you would with trying to map a QUBO with gadgets that we saw this morning?
Roughly, but the constant in front is small.
Clear, thank you.
Any other question? So, yeah, I had the same question with respect to overlapping constraints. Like you have multiple constraints all applying to, say sub-collections of qubits. Is there extra overhead to compiling?
Yes, that's true. So the way I presented it, basically, I assumed, or I just showed one line, right, which means this is something you can do. Once you have multiple intersecting constraints, this is something that Maike is actually at the moment working on. I'm sure she's here. Yes. So what you can do with all this compiling tricks and so on, you have to more or less copy your qubit that is a multiple constraint. Yes. Okay, so